Good afternoon, ladies and gentlemen. I am Duan Baoyan from Xidian University, Xi'an, China. The topic of my presentation is Fundamental Technology and Prototype Experiment of MWPT and SSPS in China. What and where is Xidian University located? Let's see the map. This is China and the capital city, Beijing. And also, this is the national geodetic origin of Jingyang County. More importantly, is that the historical city Xi'an, capital of Shanxi Province, is located here. Speaking of Xi'an, it is a fascinating city with a strong cultural atmosphere and many places of interest. The representative ones are the terracotta warriors from the Qin dynasty and Dian Pagoda from the Tang dynasty. The world-unique city wall, with a perimeter length of 13.75 kilometers, and the bell tower from the Ming dynasty. Xidian University, where I have been working since 1978, is located right here. Xidian University, under the jurisdiction of the Ministry of Education, dedicates itself primarily to the electronics and information education and research. With an integration of a wide range of academic subjects covering engineering, science, and so on. It is one of the universities funded by the central government's project named as First-Class Universities and Disciplines of the World. Project 985 Innovation Platform, Project 211, and 2011 Plan Project, so on. It is also one of the top 20 universities in 1959. Now to the main subject. Nowadays, there are mainly 4 kinds of energy wireless transmission. Let's see. Harvesting. It is particularly for the weak microwave energy collection. High-power pulsed microwave emission. High-power continuous microwave transmission, including coupling model and radiating model. The coupling model is constrained within short distance, such as ground charging pile and mobile phone wireless charging. And the radiating model can be applied in long-distance MWPT, such as unmanned aerial vehicle, remote region and disaster relief, space charging pile, and intervene typhoon track. The 4th case is microwave power and information transmission simultaneously. The following presentation is focused on the 3rd case. Firstly, the SSPS Omega 2 project. As well known, SSPS is composed with 3 parts, namely solar energy collection and conversion, microwave wireless transmission, and rectenna, accompanied with 5 energy conversion, solar energy, SE, to DC1 with photoelectric conversion, then to DC2 with power management and distribution. Next to RF1 by microwave device and transmitted toward rectenna by transmitted antenna. Afterwards to RF2 by MWPT. Finally back to DC power again, named DC3 rectified by rectenna. Since MWPT concept is submitted, several competitive SSPS designs have been proposed in the world. They can be divided into mainly 2 kinds, non-concentrating and concentrating types, as shown in these figures. As far as the concentrating type is concerned, the most interesting and competitive one is the Alpha from Mr. John Minkins. To be honest, Alpha is really a good design project and looks beautiful as well. However, investigation of it yields the following 3 shortcomings. First, thousands of hexagonal mirrors have to be timely controlled so as being oriented to the Sun while whole structure moving along geo-orbit. Second, light will leak between the mirrors, resulting in sun energy loss. Third, the sandwich structure results in severe heat dissipation problems. For the sake of this, we proposed an innovative design called CSP Omega in 2014. This project has such a fundamental innovation. The incident parallel sunlight is collected to the PV cell array. Then the DC power is transmitted to feed antenna through electric system and is finally radiated out by means of microwave wirelessly. As shown in the animation, when at the lower left position of geo-orbit, the blue semisphere is utilized to collect the solar energy. Clearly, the necessary moving part during operation is just the constant moving of line feed. Compared with Alpha, the Omega design is of 3 advantages. One is that just one-dimensional motion of PV cell array is needed. Second, there is no light leakage. Third, the heat dissipation pressure is reduced dramatically. And more importantly, the power-mass ratio could be increased by about 24%. Further investigation tells us that there still remain tow difficulties in Omega design project. One is the semi-transparent and semi-reflecting thin films to meet the requirements of forward transmission and reverse reflection, and at the same time microwave transparent. The other one is huge power rotary joint, which is of low reliability. To overcome the above 2 problems, the improved design called CSP Omega 2 is proposed. In this updated design, a semisphere is used instead of the whole ball. The solar energy is collected and converted into DC that is sent to transmitting antennas by cables instead of rotary joint. The electric propulsion system is used to keep the concentrator oriented toward the Sun. The transmitting antenna is an omnidirectional microwave antenna, which is specially designed in both horizontal plane and vertical plane to keep the beam oriented toward ground rectenna. Secondly, fundamental and technology. This section concludes 4 aspects: multi-field coupling, energy transmission, in-orbit assembly, and thermal control. First, the multi-field coupling. Among subsystems of concentrator, photoelectric, and antenna, there exists energy transfer and coupling among them. Therefore, this is a multi-system synthesis and multidisciplinary coupling system. And the system coupling model needs to be considered. At first, concentrator. In the model, sunlight pressure, structure deformation, temperature, attitude control, and manufacture and assembly errors are considered. Then is photoelectric subsystem. The IV characteristic affected by sunlight intensity distribution is also taken into consideration. As for antenna subsystem, electromagnetic coupling properties are incorporated into the model. Finally, the system coupling model can be contained by synthesizing the coupling model of the 3 subsystems. As a result, an integrated design optimization model can be expressed as this. to search for design variables such as electromagnetic, structure, and temperature, maximizing power-mass ratio whilst satisfying the nonlinear behavior constraints of performances and coupling equations, and so on. Second, energy transmission. The energy transmission from DC2 to DC3 mainly includes microwave conversion, wireless power transmission, and receiving and rectification, which can be classified into 4 technical aspects: DC2 to RF1, transmitting antenna, beam pointing, and rectenna. As far as DC2 to RF1 is concerned, there may be gravity, wind, and solar irradiation in the antenna's working environment, which will produce structural displacement, form a structure field. When the antenna unit works, the power device generates heat, which will form a temperature field. The temperature field and structural displacement field will affect electromagnetic field and decrease the transmission efficiency. Therefore, the electromechanical coupling (EMC) model can be mathematically deducted. In the model, nonlinear parameters of structure, heat and control, manufacture, and assembly are all taken into account. As for transmitting antenna, both important considerations of beamforming and highly integration are investigated. For MWPT, beamforming requires both BCE and flat beams. This depends on the amplitude, phase, and position. Take the amplitude as an example. By optimizing the aperture amplitude distribution and establishing an optimization target that takes BCE and flat into consideration, then we can obtain the results of emphasizing BCE only and emphasizing flat only, respectively. Also, the result of synthesizing BCE and flat simultaneously. Furthermore, special shape can be formed in this way. From the perspective of implementation, the APAA is adopted at present, so its composition is as follows. To reduce in self-weight and volume, the integrated technology can be applied. For instance, the phase shifter and power amplifier, as well as the power division network and radiating element. Then, the beam pointing needs to be considered. In order to solve this problem, the reverse guidance signal is used to adjust the offset back, which involves microwave measurement and pointing control. Microwave measurement includes 2 points. One is power density. The power density is measured with a probe array. The layout of probe array is well designed, and then through a multi-point measurement, we can know exactly the beam deviation. The other is reverse guidance. Based on the direction backtracking technology, the receiving-transmitting footprint alignment can be realized. There are 2 difficulties to overcome. First, the receiving and transmitting signal isolation. In transmitting antenna, the isolation problem between receiving and transmitting signals requires higher isolation degree. The second is the micro, weak signal extraction, because the strength of the reverse guidance signal is far lower than that of the transmitted energy signal. Pointing control also includes 2 points. One is mechanical control. The other is electrical control. As the animation in the report shows, accurate beam pointing is achieved with 2 aspects. Fourth, the rectenna. The RF DC efficiency is affected by rectenna efficiency and rectifier efficiency. For the rectenna efficiency, there are two aspects needed to pay attention. One is the layout consistent between rectenna and transmitting antenna, that is, flat beam to flat beam, ring to ring. Second, element consistent among rectenna elements. When the consistency performs bad, there will be high-order shock waves, and it will affect the rectenna efficiency. The other is the rectifier efficiency, which can be used in two ways at present. One is diode rectifier, which is the mainstream way at present. Its power from 1 microwatt to 500 microwatts with efficiency around 80%. The second is cyclotron wave rectifier, which can handle power range from 0.1 kilowatt to 10 kilowatts with efficiency around 80%. Third, in-orbit assembly. Space in-orbit assembly includes two aspects: inter-subsystems and intra-subsystems. For inter-subsystems, it's the assembly between concentrator, photoelectric, and transmitting antenna. For intra-subsystems, taking concentrator as an example, it's the assembly between subarrays of concentrator. These lead to the characteristics of variable structure, variable stiffness, large scale, large flexible, big hysteresis structure, mechanism, system. Therefore, the assembly sequence and vibration attenuation need to be considered carefully. For the assembly sequence, the basic idea is to connect and deploy the core ring trusses at first. Then is the concentrator assembly at multi-positions, where the concentrator element is assembled in a certain sequence. For the vibration attenuation, according to requirements of system vibration reduction, isolation, the mechanical metamaterial and permanent magnet is used to realize low frequency and wideband. Also, according to requirements of system docking, the new idea of shape memory polymer composites is proposed, including simple type and combined type. Fourth, thermal control. Heat in space can only dissipate by heat conduction and heat radiation. With a strict requirement of system mass, the efficient heat conduction, removing heat from key devices, and efficient heat radiation to cold space is a key to design. Therefore, by analogy with butterfly wing, the bionic space radiator is designed in this optimization function with mass constraint, and results have been obtained by means of this methodology. Thirdly, ground experiment prototype. To demonstrate the innovation design and technologies, we have developed two experiment prototypes, indoor and outdoor. The indoor prototype consists of a spherical concentrator, a parallel light generator, PV array, transmitting antenna and rectenna. The whole efficiency of DC to DC is up to 20%. On the basis of the indoor prototype, a bigger outside one is constructed. It is mainly composed of spherical concentrator, transmitting antenna, lifted by a 75-meter high supporting tower, and rectenna on ground. With this system, we can realize the whole chain energy collection, conversion, and transmission, and the simulation of geo-operation. Also, we have the concentrator and the gyroscopic PV array. This is the transmitting antenna. And this is the rectenna. The all configuration and the rectenna on ground have been manufactured, just like this. This is the view at night. Fourthly, the future tendency and prospects. The future work may focus on the improvements in the following aspects: the framework of SSPS, lightweight design and spatial assembly of flexible structures, high voltage, huge power DC transmission and management, microwave generation and transmitting, microwave receiving and rectification, measurement and control of beam pointing. That's all. Thanks for your attention. Question and comment.